My name is Louis. This is my colleague Konstantin. We both work at Apple, where we work on libc++, which is the C++ standard library, that comes with the Clang compiler under the LLVM Foundation, and it's used on all Apple platforms and many other non-Apple platforms as well, like Android uses it and so on. So, and we've been working pretty hard in the past couple of years on improving the security of C++ code bases. We're pretty passionate about that. And so we are really happy to be here today to tell you a little bit more about what we've been doing. Okay, but before we get started, why do we even care about this, right? So I think there is a case to be made that software security is super important nowadays, right? First of all, it is a financial threat, right? It's well known that there's the WannaCry ransomware, for example, pretty recently actually, that affected over 300,000 computers worldwide and cost over $4 billion. That's a pretty large bill. It's also an infrastructure threat because everything's connected nowadays, right? The infrastructure is not running on pen and paper, it's running on computers. So there's been examples of malware that actually targeted power stations. That's like really scary stuff, right? And finally, and I think most importantly, it's also a physical threat, right? It's pretty well known actually that there's a spyware called Pegasus that has been used to target journalists and high-profile activists just because their ideas were not really in line with the regime, and in these cases actually their physical safety was actually compromised. Like bad stuff happened to these people, and so this is actually scary stuff, I think. So that's why I think it matters so much to talk about security. Here's a fact that we know, right? It's actually, there's a lot of data about this, but memory unsafety accounts for roughly 70% of the highest severity security issues out there. So this is like the elephant in the room, right? There's a lot of reasons, there's a lot of ways that you can exploit the system, but memory safety is often in the wild one of the ways that people exploit our systems. And so that's like, if you want to go for fixing a lot of things at once, you go for that target basically. Another fact that we all know about is the fact that C++ is memory unsafe. And I don't mean it in so much in a diminishing way. It's just like it doesn't have garbage collection, it also doesn't have memory safety. It has a lot of other stuff, really cool stuff, but it's just not a property that the language was designed with and built with, right? It's just not a property of this language. And so if you connect the dots, and actually that's what they did, that's what the White House did, right? They said, well, memory safety is really, really important. And we've got C and C++ that are widely used that are not memory safe. Well, we're going to recommend that people use memory safe languages at least for critical software going forward. So essentially, it's just a recommendation, but it says a lot, I think, about the situation we're in when a government actually makes a statement about the technology that you should be using. So this is pretty serious. And so we know that there are some memory safe alternatives to C++, right? And the goal of this talk is not to get into a language war or anything, because there's also a lot of reasons why you may not be able to or may not want to actually migrate to another language. So let's assume that you're using C++. Can you do anything to make it better, right? I think we can. We can make it better, right? Because it hasn't been so good lately in terms of safety and security in C++. And that's why we're talking about it so much, right? So I think C++ can actually do better. So I'm somewhat hopeful, but I think we need to work towards that. And most importantly, I feel like we actually must do better. It's not only a can, it is really like we need to do better here. I think I've made it clear that software security is like a really important matter in terms of even just guaranteeing people's safety. So that's a really, really serious thing here. So I think we have a moral imperative. That's really how I feel. I feel like I have, as a C++ engineer, in the position of making a difference here. I think I have, and the committee has, and the C++ community as well has a moral imperative to actually, improve on the current situation. And that means sometimes shifting focus from really cool stuff over, to something else. And I think we got here, for many reasons, but I think that, part of it is an attitude problem. I don't think it's not all an attitude problem, but there is definitely, it played a part in getting us where we are. C++ has always been, an expert-friendly language, right? And some would even say an experts-only language, right? It's kind of hard to pick up. And there is a general philosophy in the language that when the user makes a mistake, it's actually their fault, right? They're wrong for, oh, you're so dumb for, thinking it worked that way, right? And often this is hidden or like buried under the sort of requirement or the goal of being like very performant, right? So it's really easy to say, oh, this API is complicated and easy to misuse because we need it to be performant. And I think, it's a little bit of a fallacy. However, the mindset is changing, right? There's a lot more general awareness about the problem. We kind of have to because the industry is reacting to everything. There has been the creation, for example, of a safety and security study group within the C++ committee to actually discuss these issues. Most of the C++ committee understands that this is a fairly, not urgent, but we can't wait too long before we start addressing these issues, or else C++ could be challenged in its relevance as a general purpose programming language. So we're we have we're making steps towards that, but in practice, we don't have very, very many concrete solutions. And the reason is not that we're lazy or that we don't want to, it's just that it's hard, right? It's like the difference between having a really great idea on paper and proposing it and actually implementing that idea and deploying it to like billions of computers or billions of devices. Like that, there's a huge difference between the two, right? And also a huge difference in terms of like investment, time investment, engineering effort. It's just a whole nother story. So I think that's why there's still a few solutions. But we've actually we've been through the cycle of doing this, a couple of times now. So I want to actually, or we want to actually present, two of the very concrete techniques that we've deployed in the wild, and talk about our deployment experience and talk about what the results were, because we were really excited about those. So first, I'm going to give a short overview of memory safety. So we often talk about the 5 pillars of memory safety. We have spatial memory safety, temporal memory safety, type safety, guaranteed initialization, and thread safety. We're mostly going to talk about the two first ones. Spatial memory safety is the notion that each allocation has a size, right? And when you access the memory outside of those bounds, you have an out-of-bounds access. That can be for reading or for writing, doesn't matter. Both of them are considered an out-of-bounds access. And so here's an example. I have this very unfortunately written program. It's a toy program. And I have 2 character arrays on the stack, and they've been statically sized because, of course, this is slide code. And what this program does, essentially, it reads a reference password from a file, and then it writes it into the password char array, right? And then it asks the user to enter the password, and it's going to read that into the input char array. Now, let's say that the user is a malicious user, and they're like, I'm going to try to write security as the password. So they enter security. So first, we read into the password variable. Then we read the user input, and we start by reading security, but std_cn will read until it hits a new line. So we actually keep reading. We actually keep reading until we hit the new line. But at this point, we are out of our char array, of the first char array. And we're actually writing the bytes in memory that are the next variable in the stack, right? And the next variable in the stack is the reference password that we just read from the file. So from the perspective of the program's state of memory, the reference password and the password you just entered, the user just entered, are the same, right? And so this actually highlights something interesting about, this is the way that attackers look at your code. They look at your code as basically a giant state machine, and what their goal is to get into a state of the memory of your program that they can use to do something interesting, like maybe call a function you never thought would be called with parameters you never thought would be provided, and but they're all doing all of that under the privilege level of the program. So that's basically how they're thinking about this. How can I provide a twisted input to get what I want out of the program? Then we have temporal memory safety, which is the notion that all accesses to an object should occur during the lifetime of that object. So think about like dangling pointers. That's basically what it is. And if you access an object outside of its lifetime, it's called a use after free. So it's basically a dangling pointer bug. This usually composes with type safety. So we have, type safety is the notion that every memory allocation, every part of memory actually has, a specific type. It's the type that you allocated the memory for and, that you put in there. And when you interpret that location in memory as a different object, you have what we call a type confusion. It's like, as if you like reinterpret cast a pointer to the wrong type and you access it as another type, you're going to interpret these bytes maybe as something they are not, right? And so most use after frees actually require also a type confusion. So the holy grail of most attackers is going to be something like this. You have a type that represents data, maybe a timestamp, maybe like a char array or a string, and you have a legitimate API that allows you to modify that data. Okay, so let's say you can set a timestamp on something, and then you know that the program that you're interacting with actually has a bug in it, and that the legitimate API that you have is going to write through a pointer that is dangling, right? And you know that another important part of this program also has a structure, right, of interest to you that happens to be allocated in that exact spot of memory where the dangling pointer is. So now what you do is you actually use your legitimate API to, let's say, set the timestamp to an arbitrary integer, and you're actually overriding the pointer in that other data structure. And then you just let the code run, and eventually when the code reads that pointer, it's going to dereference whatever you put there as an address, right? And so that's basically, how these things work. Of course, more complicated, but that's the idea. And you can imagine this gets really scary if you have like a function pointer, because now, if they manage to actually write an arbitrary address, instead of that function pointer, you're just like transferring control to the integral value that they input on the, command line or whatever. So it gets really scary. And so to tie it back to ISO C++, it turns out that actually not all, but very, very many of these issues have sort of a name for them in the standard, and they're called undefined behavior. And so I'm actually going to pass it on to Costa, who can do a deep dive into library undefined behavior.
Thank you, Louis. So if we turn from the real world into the more abstract world of the standard, we'll find that all memory safety issues, and in fact many other classes of bugs, are all under this very generic term of undefined behavior. And probably we all encountered that infamous definition of undefined behavior at some point. This is the behavior for which this document imposes no requirement. So when undefined behavior happens, theoretically anything can happen. But in reality, we know that within, on a particular platform, within a particular context, it's not anything, it's something specific. And in general, it would be pretty useful for us to impose a little bit of order on this chaos and do some classification of this umbrella term of undefined behavior. So first of all, it would be useful for us to make a distinction between what we can call a language level undefined behavior and library level undefined behavior. And the difference is essentially for the language UB, it's when the compiler is free to do whatever. And for the library, it's when the standard library is free to do whatever. And these two subsets are not of an equal size. Library level UB is actually a much smaller subset of the total undefined behavior, and for a few reasons, it's actually easier to deal with. First, most instances of library undefined behavior are very explicitly stated in the standard. This example is the stud span indexing operator, it has this nice precondition that the index you pass to this function has to be less than the size. It's as explicit and straightforward as it gets. And the total all the standard library functions and classes are listed in the standard. So the total number of instances of undefined behavior in the library has an upper bound. And assuming a perfect implementation, like we're dealing with the abstractions here, library undefined behavior can only happen due to user input. So in essence, we have these well-defined particular places in the library where user code invokes a library function, and that's the only places they are enumerated where undefined behavior can happen in the library. So all in all, it means that library UB is much easier to check than language UB. And another ways of classifying that we can introduce to make it, granularize it further is we can classify library UB by severity, and it ranges all the way from benign within a particular implementation, of course, to security critical, and by critical I mean an attacker can gain arbitrary code execution on your machine. And the other axis is how difficult it would be to validate this case of undefined behavior, and that ranges from trivial, like the Stutzpan example we just saw, to impossible. And I mean not just practically infeasible, but I think in some cases it's literally impossible for some semantic requirements. For example, many sorting functions have a semantic precondition that the a comparator you pass to it imposes a strict weak ordering. Given that the comparator doesn't have to be pure, I don't think it's possible to 100% prove that it always imposes a strict weak ordering. So that means that even in a perfect world within an implementation, we cannot eliminate like all cases of library undefined behavior. So we have to pick our battles. And in fact, there is a quite significant overlap between cases of UB that are security critical and cases of UB that are trivial to check. And this set intersection is where we should focus on. And going back to that definition of undefined behavior, you know the joke how you can look at the glass of water and say that it's half full or half empty. Also, we can say that when the standard says anything can happen, it doesn't necessarily mean that something bad can happen. Something actually useful can happen, and we can turn UB into useful implementation defined behavior, and that's essentially the idea behind library hardening we do in libc++, to turn UB into useful implementation defined behavior. So this is like the main points of what we call hardening in libc++. We turn select UB into guaranteed traps. So select, remember, we just saw that we cannot handle all undefined behavior, so we have to be picky about what we focus on. And a trap is an instruction to essentially terminate the program as fast as possible. And the important part that it's guaranteed behavior, which eliminates the scariest part of UB, like you don't know what can happen. If hardening is enabled in our implementation, you know you get a guaranteed trap in this case. And we provide several different hardening modes with high-level semantics, and then users can select the mode that makes the most sense for their project and their particular set of constraints. And the platform vendors can select the default mode for the platform, but then individual projects can override that mode. And we have just 4 different hardening modes with the idea that this set should be as simple as possible, but no simpler. So first is none, which is essentially the status quo, the mode where we don't compromise any runtime performance. And I want to stress that library hardening is all about runtime checks. If it's something that can be done at compile time, we generally just do it. So because we are focusing on runtime here, we have to pay a lot of attention to overhead. Then we have the fast mode, in which we only enable security critical low overhead checks. And we try to keep this mode as lightweight as possible and set the bar really high for any check to be enabled in this mode. Then beyond that, we have the extensive mode, where we drop the requirement that the check has to be a security critical. If it's low overhead, constant time check, it has a very good, it's a very good candidate to be enabled in this mode. And then finally, we have the debug mode, where we simply enable everything that we have with much less concern about the performance overhead. And they say that a picture is worth 1,000 words. So before we go further, I wanted to give a very simple example just to make it a little bit more concrete how hardening works in practice. And this is a toy program. It is, of course, pretty contrived. So here we have a program that expects to receive a single argument on invocation, and it interprets that argument as an integer. And that integer is used as an index into a pre-populated vector of strings, and it would print the string with the corresponding index, and it even has a check that if you give it an incorrect index, it would print not found instead, but this check is actually wrong. If you look at it, like it's, of course, a pretty contrived example, but this is a kind of error that does happen in reality under more complicated circumstances. So the use of S size should draw your attention. So consider what would happen if you pass a negative index to it. It would actually pass the check because the negative number would be smaller than any size, but then when we do the actual indexing, it would get reinterpreted as a large unsigned number, and we would get an out-of-bounds access. So if we were to run this program with reasonable index, we would get some reasonable output. But if we were to run it with, let's say, -1, in this particular run, I got empty output, but really it was whatever happened to be in that memory location at that very large incorrect offset. But if we were to recompile this program with hardening enabled and run it again, then instead we would get a trap, which is to say that the program would crash before it has a chance to access memory out of bounds, which is great. Like, it's much better to reliably crash early than to compromise the memory safety of your program, where you can end up in a state where an attacker can do anything with your machine. And if we were to run this with a debugger attached, we would also get the error message. It's maybe a little hard to read the red text on the black screen, but it's, basically it says vector index out of bounds and stack trace. And so this is like for a very quick overview, and to move on to some ideas behind the design, there's one that I want to stress in particular. This is not just a debugging feature. This is intended to be enabled in production. You should ship your project with hardening enabled. And this really is what distinguishes it from similar previous efforts, including in our own libc++ implementation. And in our experience, in our view, it really is not enough for these kind of checks to be enabled only when testing, only in debug mode or something like that. And we've had those kinds of tools for a long time, for many, many years, and they're great, they're useful, but if they were sufficient to really solve the memory safety problem in C++, we wouldn't have the White House report, and frankly, we just wouldn't have this conversation today. So clearly, though, that approach is not sufficient. That's why we want hardening to be lightweight enough to be usable in production, and really many things in the design follow from this priority. because in the real world, different projects have different requirements and make different trade-offs between performance and security. And really, during the deployment experience, we heard very clearly from two broad camps. One camp of projects where performance is critical and they really can't afford anything more than our very lightweight fast mode. And the opposite is the projects that are less concerned about performance, but are very concerned about security and just general program correctness. And those projects generally much prefer the extensive mode, which has more checks. And even within the same project, usually the most performance critical parts of the codes are relatively small and can be isolated. So even this applies even within a single project. And for picking what to prioritize, the 80-20 principle really helps. We know that most of the most serious issues are caused by just a small subset of types of bugs, and specifically the memory safety bugs. So we can say that we get most of the benefit by focusing on just a relatively small subset of checks. And also adoption is crucial for hardening to succeed and make a difference in the real world. So I personally feel that having many projects adopt lightweight checking makes a bigger impact than having just a few projects adopt very extensive checking. So this is for an overview of the design ideas, and to give now turn to the implementation. So first of all, it would be pretty unmanageable, pretty hard to reason about if we were to map checks directly to the 4 hardening modes that we have, because, well, we have a few hundred checks. It would be very hard to say what does the extensive mode, for example, mean if it consists of, let's say, 300 checks. And you know the saying that every problem in software development is solved by introducing an additional layer of abstraction. We group checks into categories, and the criteria for the grouping is roughly what's the bad thing that would happen if this check were to fail. And we have categories of the nature you might expect, like a valid element access for making sure that when you access a container element, it is within bounds. Valid input range to make sure that when you call a function with a range as an input, that range is actually valid, like the end is reachable from the beginning. That the given pointer is not null if it's not supposed to be null by the precondition, and so on. And this is really our internal abstraction. We only expose the hardening modes to the user. And this is an example of how the valid element access check looks like in our implementation, and it affects containers. It also affects types that could be seen as a container of at most one element, like optional or expected. And a similar example is there are a few functions usually dealing with copying that take an input range and an output range and have a precondition that those ranges do not overlap, so we also have a category for that. And then those categories are grouped into modes. So modes are collections of categories, and for the non-mode, unsurprisingly, we don't enable any categories. Then for the fast mode, we enable a valid input range and valid element access, so basically the categories that deal with memory safety. Then for the extensive mode, we enable a few more on top of that. And finally, for the debug mode, we enable everything, including our internal assertions and semantic requirements, which can be quite costly. And you can see here that each subsequent mode is a superset of the previous mode. So it contains all the checks from the preceding mode and then some more checks on top of that. And hardening is the mode is chosen at the compile time. You cannot change it at runtime. And currently, the way to enable is by defining a certain macro. So you define libcpp hardening mode to a value which corresponds to the mode that you want to use with the names you would expect. There's a macro for none, for fast, for extensive, and for debug. And some IDEs might provide a nicer visual UI on top of this. And also, we really hope to eventually add a compiler flag for this. And hardening modes can be chosen on a per translation unit basis. So even within the same project, you can have different hardening modes enabled in different parts of the project. And when a check fails, the program is guaranteed to terminate, but how exactly it happens depends on the mode. For the production-capable modes, with fast and extensive, we immediately trap. So trap is just a single instruction to stop execution as fast as possible, and it's great from the performance perspective because it's just one instruction. There's no external function call. It's easier to optimize for size. And also, it's good from the security perspective. There's no additional error handling code involved that could potentially involve other bugs, and it's not overridable by the user. But for the debug modes, we prioritize user experience, so we do something different. Instead, we print the error message to the standard output, which we don't do for production modes, and then we call abort. And for any proposal to add something new to C++, the elephant in the room is the ABI. What about the ABI? Let's consider this example with a span. Let's say we have this span of 3 elements, and we create an iterator, and then we try to access an element way out of bounds through the iterator. Would this incorrect access trap if hardening is enabled? And the answer is it depends. It depends on the current ABI configuration, because this kind of check would require ABI change. It would require the iterator to somehow store information on what is within bounds. And this is really a very important part of our design. We decided that the ABI is completely orthogonal to the hardening mode. These two are independent. And the reason in here is that the hardening mode is a property of a particular project. It is selected by the user, whereas the ABI is a property of the platform, and it is chosen by the platform vendor. And encouraging users to change the ABI relative to the rest of the platform is just a recipe for disaster. So instead, the model here is that the hardening mode enables all checks that are possible within the current ABI configuration. And then we provide a few ABI configuration macros that can enable additional hardening checks. So for example, for bounded iterators, we have this libcpp ABI bounded iterators, and if the vendor of your platform enables that in the ABI, then for a few types like span, for example, we would use our bounded iterator implementation as the iterator type, and then that access would actually trap, but only if hardening is enabled, because remember, these two are orthogonal. You can have bounded iterators enabled in the ABI, but if your hardening mode is none, you still get no trap. And it might be a bit of a niche case, but it's actually useful for people to be able to, for example, temporarily disable hardening regardless of what their ABI configuration is. And to give just a small particular example of something I found pretty neat, sometimes you might be surprised of what is possible without an ABI break. So consider a unique pointer over a dynamically allocated array. it would seem that you need to store the size of the allocation inside the unique pointer object to be able to check bounds, and in general it's true, but often we can avoid that actually because there is something called the array cookie. It actually depends on the particular ABI, but it's true for Athenium. And we can rely on that instead of storing the size in our pointer object. And this code is a bit complicated, but the idea is actually simple and it's easier to show visually. So we might imagine that when we call, let's say, new for 5 objects of a certain class, that the compiler would allocate a space for 5 objects and then call the constructor 5 times. But in reality, it allocates some extra space at the front. And that space is used to store the size of the allocation, and this extra storage is called the array cookie. And this information is later used to know how many destructors to invoke. And since we're the implementation, when we can rely on this, we can also unpack that array cookie and use it for bounds checking. The hardening has been available for 2 upstream releases of LLVM, and our deployment experience has been pretty positive. At Apple, we have several projects that enable hardening, including really major ones like WebKit, which is the basis of the Safari browser, and XNU, which is the Darwin kernel. And we also have adopters at Google, including Chrome and also Google Andromeda, and we were very happy to read the blog post from Google that described their experience with enabling hardening in Andromeda, which is a performance critical project, and they were able to achieve a pretty low overhead by selectively disabling hardening around the hottest parts of their code. And already we know of some past in the wild security issues that would have been prevented if hardening was enabled, or at least would have been alleviated. But in many cases, enabling hardening can be really as easy as recompiling the code with some specific hardening mode. But to paint a full picture, there are some caveats you should be aware of. So I think the most important one is that, well, we only harden the standard library. So you get as much benefit as you use the standard library. If your project uses custom types, or if we're dealing with the C-style code that doesn't use the standard library much, well, you don't get much benefit. And to get the benefit from hardening, you would have to rewrite the code to use types like studspan and studvector, and of course that also risks introducing new bugs. And also, as much as we try to keep the performance overhead as low as possible, it still is not zero and cannot be zero. So if your project is performance sensitive, you would want to measure before enabling hardening in production. And so far, we've been talking about what we are doing in our implementation. So this is all like implementation defined guarantees, and it's great. But one of the strengths of C++ is its portability, and also going back to White House reports and similar things for people who write security guidelines or people who follow those guidelines. It matters a lot what the actual standard guarantees and not just a particular implementation. So we strongly feel that this would be much more useful if it was a part of the standard. And there definitely is a certain momentum to reduce the amount of language undefined behavior in the standard. That there was a recent proposal related to uninitialized objects, and we really hope to see a similar momentum for reducing the amount of undefined behavior in the standard library as well. And to that end, we recently published a paper. You can see a link on the slide. It's called Standard Library Hardening, and it's really to provide a subset of the guarantees we have in libc++ as part of the fast mode in the standard. And the approach is, like we saw before, that many of those checks are already in the standard in the form of preconditions. Just take the most valuable of those existing preconditions and turn them into hardened preconditions. And then a conforming implementation would have to provide single hardened modes. We don't propose to add all our 4 modes to the standard, just one hardened mode that guarantees to check those hardened preconditions and terminate the program if they fail instead of triggering undefined behavior. And going back to the span index and operator example, it would look just like this. We just slap the words hardened to the preconditions section, and that's essentially it. And the reality is that there's a lot of code, C++ code out there that is security critical, that is important, and that just is infeasible to rewrite for many reasons. And we feel it's very valuable to look for ways to improve the security of existing code without requiring any sort of extensive rewrites. And we hope to see some progress on that front, and also some progress on reducing the amount of undefined behavior in the standard in general. So that's all I wanted to say about hardening in the library, and I'll hand it back to Louis. Thank you.
All right, so we had 2 techniques, so this is the second one. So I want to talk a little bit about, so we talked, about temporal memory safety, and this is what this technique is about, right? It's about typed memory operations. So when we talked about temporal memory safety earlier, I mentioned, right, that most of the dangling pointer kind of issues required being composed with a type confusion of some sort, right? So we can actually make a very clever observation. If you never allocate, right, the memory for 2 different types in the same location, even if you have a dangling pointer bug, it may not be exploitable, right? So in other words, let's say the attacker finds a dangling pointer bug in your code, and they're like, oh, if that foo is aliasing a bar, I know how to take over the control of your program. But if you never ever allocate a foo and a bar in the same region of memory, this can never happen. So you still have the bug, but it cannot be exploited. So that's what this technique exploits, essentially. And so the idea here is to isolate the allocations by type, right? To make sure that you don't allocate different types in the same region of memory ever. And this was utilized in the Darwin kernel a few years ago, and there's a really interesting article explaining what they did. And so this is basically what a naive type memory allocator would look like. It's the allocator. It has a bunch of pools, one for each type. And when you ask it for a foo, it gives you memory from the foo pool, right? That's basically it. Now, of course, it doesn't quite work that way because it would be too inefficient. It wouldn't work. So you actually have to bucket several types together sometimes, right? But it's a game of which types can I most safely co-locate, right? So what you're trying to do is come up with some sort of hashing function, or mapping function from types to buckets that creates the least number of interesting overlays for an attacker to abuse. So that's the general idea. And the most important property that we can come up with here is really that types that represent data, like an integer or a string maybe, should not alias pointer-like types. So a pointer or a function pointer is a great example. Anything that's used for control in some sense, right? Either you jump to it, or maybe even if you often use branch on this bool, for example, you might want to avoid actually allocating it with or co-locating it with some data, because those are the type of things that attackers look for. If they can override this pointer, this function pointer, or this bool, they control the branch that you're taking. Therefore, they just told you where to go in your code. So this is the most important property. And there's a bunch of stuff we can do, like we can randomize the buckets on boot, and we can do very, very fancy things to make it extremely difficult and really painful for an attacker to actually exploit a bug that they find. But that's the general idea. And we actually have data from the Darwin kernel that says, that suggests that the vast majority of dynamic allocation lifetime bugs actually, are not exploitable anymore when you do this. So this is really, really effective. Of course, it's a evolving threat landscape, so it changes all the time. But this is what we've been seeing so far. And so our goal here is to bring this technique, right, to C++, for general C++. We want basically the cool technique that really improves security, but with the ergonomics that we have in C++. Because otherwise we're going to have to rewrite a bunch of code. It's going to look like crap, and we don't want that. So our goal is that when you have a new expression like this, it should be allocated from the foo pool, from that types pool. So if the user to understand how that might work, we have to step back and look at how a new expression is actually, desugared by the compiler. So when you have a new expression like this, what the compiler actually writes is a call to operator new, where it passes the size, and then a call to the constructor of foo within that allocated, memory. That's basically what happens. But the problem is that there's no type information anywhere, right? So there's no way, operator new cannot possibly pass information down to the system allocator about what type it's allocating. It doesn't know it. You have the size, you have the alignment. So you can deduce a few things, but not much really. So that's the problem we have. But we are the implementation. So we surely can add a new operator new, right? So this is actually what we did as a vendor extension. We basically added a new private, please don't use it, but a new private operator new. And it takes a type descriptor T, which is essentially an integer, a very magic integer that you can think about as a very simple type info sort of object, right? But it contains information that is relevant for a system allocator to know how I should bucket that type, essentially. And if we go back to this desugaring, essentially this vendor extension has a rewrite where when you say new foo, instead of calling the operator new with just the size, it actually passes this this built-in type descriptor, this type descriptor that contains additional information. That's it, right? So you just recompile your code, and whenever you had new blah blah blah, the compiler is just gonna without telling you, just gonna generate a call to a slightly different function with a magic argument. We can do that. The compiler can totally do that. So from the implementation, it's really simple. It's a C++ standard library, right? We don't do many clever things. We mostly funnel down to the system, right? And so, so this is what we do. We get the type descriptor, and we then turn around and just pass it down to the system allocator. We have a special malloc which understands this type descriptor and does all the heavy lifting really. And yeah, so it just we just pass it down essentially. So by creating this rewrite and this additional declaration of operator new, we basically just created the ergonomics to power essentially the technique that is really implemented down there it's a system provided capability. And so we've actually deployed this in the Darwin user space system libraries. And it's really effective, and it's also really easy. You just flip the switch pretty much and recompile your code, and you get this essentially for free. There's a few cases where you have to be careful if you were replacing operator new, and there's a few funky things you have to care about. But by and far, it's flip the switch, recompile, and you're done. So this is actually really cool. However, it's of course not a silver bullet, right? Sometimes people will kind of work around the type system in their allocations by allocating a char buffer and then placement newing into it. So in these cases, the system allocator thinks that you allocated a char array, right? Not a foo. So we can't really do anything about that one yet. And the other thing is that the effectiveness of this whole technique relies on the quality of implementation of the system allocator, which, like I said, is a security and performance trade-off about the quality of the bucketing. Actually, even the presence of this bucketing allocator. Not all systems have that, of course. So it's a cool technique, but it's not a silver bullet. And we are proposing a standardization path, which we think provides a lot of other benefits. So this is in P2719, where basically previously, if you had a new expression, the compiler would roughly, the rules are much more complicated, but roughly what happens is that it would call either the in-class or the global operator new with the size and the alignment, maybe, and a bunch of arguments. And we're basically adding an additional tag argument at the front. We use type identity of t, right? And the compiler is going to pass that. And if this call resolves, basically it's going to call that instead. So this gives users the ability to define an operator new like this, as a template, for example. And so you get past the type descriptor for t being the type that gets allocated, right? So this is like a different way of overriding operator new that is not based on like link time a replacement that is global in the program. This is just based on like templates essentially. A really cool thing actually is that if you mix that, for example, with reflection, you could potentially say, well, I want this operator new to actually apply to all the types in this namespace, for example. So let's say you have a library or some application code and you want to replace operator new just for these specific types. You could actually do that if we have reflection or other tools. And why do we actually want to do that, right? Because we haven't done much so far. I guess we haven't solved our problem. So really, like standardizing this for us would be a way to not to standardize the whole feature, but to make it extremely easy for any implementation to actually implement this. So we could provide like a fallback operator new, typed operator new that does the built-in type descriptor magic I talked about before, and that would not require any, like this would be totally standard, modulo the weird attribute. But so essentially, like it makes us that close, for any implementation to be able to support that sort of stuff out of the box. So this is really cool, and it also allows users to implement their typed allocation scheme if they want to, either for performance or for safety or for whatever, right? Okay, so to conclude, we talked about standard library hardening, which tackles mostly spatial memory safety, because that's the by far the most important one, and it may require adoption to be effective. It really depends on what your code base looks like. If you have a C with classes code base, then you may have more work, but otherwise it's pretty much a flip the switch, recompile, and have fun. It's great for bug finding, but it's really intended and designed to be run in production. That's like really important, and we're hoping that this actually helps move the needle a lot more than all the previous things that have existed. And we are pursuing a standardization path. We hope that ISO C++ is excited to make this a portable guarantee, and we don't want to say that like all implementations are always hardened. We want to force an implementation, like a standard library, to offer the possibility of being hardened. That's what we're after, right? And so that way, people could say, well, I'm using, the hardened variant of C++. And that's, just a little bit trying to move the needle, just a little bit. And you can actually try it out. It's been released since LVM 17, I think, so a little bit over a year now. And we're always adding new checks and, improving also the performance with, figuring out, okay, the compiler doesn't quite understand this, hardening construct, so how can we rewrite it to make sure it hoists it out of the loop? And like we're always working on that. It's, always a work in progress. So if you enable it today, it's not going to get worse. It's just going to get better. We also talked about tight memory operations, which makes temporal memory issues harder to exploit. So just to be clear, this does not actually fix any of your dangling pointer bugs. You still have to go and find those. But it makes it harder for an attacker to actually take over your program based on that. And it's basically non-intrusive, which is a really important property. I know we've been talking a lot about that, but like the ease of adoption, this one is like really easy to adopt as well. And we're proposing a standardization path that has other benefits that we think are quite interesting. And so one thing, we've talked about it, but I really want to drive it home. There's a huge amount of C++ code. There's like a lot of C++ code out there. And a lot of it is not safe, or even, I think, not even good by our standards today, right? And so I think we need to do something about it, right? Like, we really have to do something about it. It's there to stay, right? And we just have to find ways to kind of make it less of a liability. And so with that in mind, like, ease of adoption for any security-related feature is the number one priority, is like the most important property of any feature, any proposal, is by far like the ease of adoption. We'd much rather enable a new feature that solves very few issues, but to enable it everywhere, than to like deploy something that makes your program formally safe, but like to do it in just one program somewhere. The impact is not at all the same. So for us, I think the ease of adoption is the number one most important thing to look for. And so this talk can be a little bit of a downer sometimes because we all love C++, right? And this makes it sound like, oh, what's going on with... I think that we can, like, to be hopeful, I think we can actually achieve better safety and security in C++, right? I think it is definitely possible. But I think in order to really be successful at that, we need to look for simple and high impact changes. We don't want to be chasing, dreams of like making C++ into something that it's not, right? Like, if you want to make C++ formally memory safe, like, there's already options for that, and they probably do it better than C++ could ever do with all of its, legacy and all of its other properties it has. So I think, like, we're really encouraging people to focus on simple, high impact changes and immediate solutions, especially from, the C++ committee. We would like to see more work towards these kind of immediate solutions, rather than, focusing on the sort of theoretical, perfection that we might or might never achieve. So that's kind of, our take on this whole thing. And finally, I want to end with this. This is actually something that I heard David Senkel say in a talk, and it really, like, I thought it was really good. So I want to share it. I think that, it's important to remember that we're not C++ engineers. We love C++, like, I love C++, right? But we're software engineers, right? And it's important to remember that, and to think about the greater good of the industry, the greater good of society as well, and to be very pragmatic about our technology choices sometimes. So that means sometimes, figuring out what is the best tool for the job, and maybe, I need hardening there. Yes, I'm going to give up a little bit of performance. Maybe sometimes it means like, I can't use C++ for this specific thing, So it's just about being very pragmatic and very mature about, technology choices. I think this is something that we need to, really do now. So yeah, thank you. We're going to take questions.
Thank you very much, Louis. We have a question from the online track. Is from Xavier Ventura. He asks, is this something you use in production code? Did everything work out of the box, or did you encounter unexpected problems in real-life code?
This is something that we do use in production code. Costa mentioned like some of the deployment experience. So it's running, in parts of the kernel. It's running in some user space libraries. It's running in, WebKit, if I remember correctly. It's running in Chrome as well. They love it, and Andromeda. So and probably like many others that we just don't know about. So yes, it's totally like you probably it's probably running on your phone right now if you're using Apple and Android. So definitely. And have there been any deployment issues? I mean, certainly there is some stuff that we've come across. There is performance problems in a few cases where, hey, this is a really hot loop. It does not quite optimize the way you'd like it, so you got to be careful. Like, we're engineers, nothing's going to be for free, right? But they're all not insurmountable challenges. And the other type of issue that we've seen is sometimes what used to be benign undefined behavior, like accessing, for example, you want to get the one past the end element of a std array, so you just say like ampersand array and then the number of elements. Well, that's technically UB because you just, you indexed it past the end. It's an off by one error. And it used to kind of work because the compiler would just optimize, everything and say like, okay, sure, you're not dereferencing that anyways. So but now it actually traps because you're calling, because you're running into this trap. So for these sort of things, yes, sometimes it can be a little bit of a challenge, but like we've had a pretty good experience with that.
The memory bucket approach sounds very interesting. Now, let's say I can't change the standard library for my project, and let's say I don't want to wait for the standardization process to finish and the compilers to catch up. What would you think about an approach where I say, okay, I identify places in my code that really need hardening and create some, let's say, hardened types, for example, for incoming network data, processing that, so that they are completely separate from any other types and they use their own memory pool?
I think you could do that by, for example, by defining a in-class operator new for these classes that are, very critical to you, I guess, and making sure that those get allocated in a special way. So I think that's doable. You can even probably define like a macro or some sort of thing that you like stick in all the classes that you care about that defines the right in-class operator new, operator delete. So anyway, that's just food for thought, but it's possible. The ergonomics are not like we're going for better ergonomics than that, but this in the current world, this is sort of the way that people have been approximating this.
So thank you for your talk. I have a question about the implementation of the hardening macros. So how do you avoid ODR definition violation, one definition violations if there are multiple translation units using different hardening modes? Is this a technique that's only available to the standard library because it uses some compiler internal stuff, or could I use the technique myself for my own library?
I love this question. No, seriously, it's a topic I love. It's twisted, but I love it. So, okay, to be really, to make things simple, basically, we use an ABI tag, which is an attribute that you can also use on your own functions. It's really painful to do, but you can do it. You just have to annotate all the functions that you want to harden against ODR violations. And we include the hardening mode, exception, whether exceptions are enabled, and a couple other things like the version of the library. We include that in there, which means that basically if you're compiling two different translation units, and let's say they have a different hardening mode enabled, when you link these two and you're using like vector operator bracket in both translation units, right? So normally the problem, if you're not careful without any ABI tag, let's say this TU has hardening enabled, this one does not. So there is a copy of operator bracket here that has a trap, and there's a copy of operator bracket that does not have a trap. The way the compilation model works in C++ is that when you're going to link those, right, the linker is going to make a choice. It's going to pick one function to survive at random. And it has the right to do that because by the ODR rule, by the one definition rule, there must be one and exactly one definition of the function. And if there is more than one, then they all need to be the same. But in this case, they're not the same because one has a trap, one doesn't, right? So you can end up actually in where you think you're calling a hardened operator bracket, but really, the linker decided to pick the one without a trap, and now, you don't have any hardening. So to work around that, we use this ABI tag, which changes a symbol name. So from the linker's perspective, they are different functions, right? So they actually the linker doesn't see the same function and says, oh, I need to ODR dedupe those, right? It actually sees different functions with a different name, and so it keeps both in the binary. So this allows you to safely mix and match hardening modes, exception, on, off, different versions of libc++, and whenever we hit like a nasty issue, we throw it in there, and yeah, it works pretty well. I think we're the only library that does that actually.
Thank you for your talk. I have just one question, and I love the standardization, but we all know that we're going to retire by the time it makes to the standard, right? So my question would be that, how far you would like to backport it? What would be the earliest version of STL? What would be available with your updates? And I give you an example. So we are in automotive, C++ 14. So is there an option to ship the hardened versions of your STL, for example, for C++ 14? Is it going to be available as an open source, which we could probably take over? And I guess you get the point.
Yeah. So hardening, all open source. It's all open source in upstream Clang. It works all the way to C++ 03. So like it doesn't, the standard mode doesn't matter. And we're very pragmatic, right? We are going, we went after this and we said, look, we need something, we need it right now. This is like, you know, coming from high up, like we need to, you know, solve this problem right now. So we fixed it, and now we're, you know, proposing a standardization path. So we're doing our thing, whether or not basically the standard likes it, you know, because it's too important, right? And so, so you do get hardening today in all standard modes as an implementation extension, basically. We would like, of course, to standardize it for C++ 2026, I guess, but you know, we'll see how that goes. But you know, you still get everything we talked about today. You get it, like you can get it now in all the standard modes.
Sorry, can we just hold it there? We're over time, and I'm sure you can ask the question first.
Thank you.